Hi, this is going to be a lesson on how to handle and work with data in measurements and calculations. We're going to do a couple of things in this lesson today. We're going to define significant figures, like what is a significant figure, and we're going to look at measurements that you take or maybe numbers and measurements that other people provide to you in a data table or in a word problem, and be able to tell how many significant figures are in that piece of data or in that number. And then we're going to do some calculations with those numbers and show you how to round off your answer to have the proper number of significant figures. So let's get started on that. The first thing we want to do is just have a definition of what is a significant figure. It's all the numbers you are certain about in a piece of data plus one estimated or doubtful digit. Every measuring tool has some type of, let me get a little highlighter here. Just use this one. Every measuring tool has some sort of like scale. And as you can see here on this scale, okay, the small markings are the millimeters and the larger numbers are centimeters, okay? So when you read this scale on this measuring tool, the markings that are in between are tenths of a centimeter. We can be certain about their value because they're marked right on the measuring tool. But if we go to the second decimal place, hundredths of a centimeter, they are not marked on this measuring tool. So we actually have to make a bit of a guess about those. And if you take a look at this line, let's say we were trying to, take this line right here and measure the length of the line. I tried to line it up to 0 on this end. And on this end, you can see that it falls in between the 7.8 and the 7.9. I just had trouble drawing a straight line up and down there. It's a little past the 7.8. Like it's definitely 7. And it's definitely past the 0.8, but it's not to the 0.9. So let me erase this and see if I can do a better job on drawing a little line in there maybe. Let's put in a different color. It's a little tough to draw that straight up and down. Like if I were, well, there I got right on the 0.9, but you can see, like I haven't quite caught the ends of that. Yeah. Oh boy, I'm having a little trouble. Do not want to end the show. So do you see that? Like I still haven't quite caught the end. Like what I would do if I was measuring this would be to, line this up exactly next to it. And I can see that it's 7.8 something, but it's definitely not over here on the 7.9. So I honestly think that it's like not even halfway. I'm going to say like 7.83. Maybe you were thinking 7.82. Maybe somebody else was thinking 7.81. And that shows how this right here, this is our estimate. And there's some doubt about it, right? It's an estimated number. So the number of significant figures in this measurement, okay, is equal to 3. Because we have the 7 and the 8 that we're certain about, and then we have the 3 that is an estimated digit. So let's take a look at the significant figure rules. Okay, all non-zero numbers are significant. So 7.83, they're all not zeros, and that was centimeters. Okay, so over here on the side, I'm going to list the number of significant figures in that measurement. It has 3. Even if it was 2.68, it doesn't matter what non-zero numbers they are significant. If that measuring tool was longer and we had a measurement like 32.85, that's 4 sig figs, because you count each one of the non-zero numbers. So the big question is then, well, what about the zeros? Okay. The 0 is the one that sometimes gives people trouble because it depends on the location within the number. Now, if you consult your textbook, there's a set of rules that says, if it's before the non-zero numbers and after the decimal point and between non-zero numbers and things. So look, there's 3 places that 0 can be in a number. Think about it. Okay, I'm going to switch to the highlighter. 0 can be before the number, 0 could be in the middle of the number, or 0 can be after. It can be at the beginning, in the middle somewhere, or it can be at the end. It's the only 3 places that it can be within the number. So we have just a way here, a little like rule or saying to help you remember when it's not significant, when it's always significant, and then when you have to be concerned about the decimal. So if it's at the beginning of the number, it is never significant. Okay. What's an example of when it would be at the beginning? Okay. So let's say we have this 7.83 centimeters, but in our calculation in the problem, we need this to be expressed in meters. So we learned our, I hate when that happens. Sorry about it. The wrong thing. You know what? I'm start over here a second. Hold on. So 7.83 centimeters. We learned how to do our metric conversions. We know that a centimeter is 10 to the negative 2, or 0.01 meters. Okay, it's 1/100th of a meter. So I multiply that and I get 0.0783 meters. See, moving the decimal and putting this number in a different unit doesn't change the instrument that was used to get the number. This still has 3 sig figs, just like it did when it was expressed in centimeters. Now, one of the hints that I'll give you at the end, and I'll come back and do that, is if you put numbers in scientific notation, sometimes that makes it easier to see the significant figures. We'll come back and take a look at that in the end. Embedded zeros are always significant. What do we mean by an embedded zero? Well, what if that line had been between the 7.0 and the 7.1? And then it might be 7.03 centimeters. Well, that has 3 significant figures. This is an embedded zero. It's between the 7 and the 3. And then what if the 0 is at the end? This is the one where you have to worry about, is there a decimal or not? Trailing zeros are only significant if there is a decimal point specified. Okay, so let me give you an example. Let's say that this line that you measured right up here was exactly on the 7. If you only wrote that, remember that the data that you write, the last number is estimated. This looks like you had to guess at the 7, like you really didn't even have a measuring instrument. You need to put the point, even if it was right on the 7, you need to put the 0.00 centimeters, because what this tells someone when they look at this, and it has 3 sig figs, is yes, I used a measuring instrument where I could read the ones, I could read the tenths, and this is my estimate. That's the reason for putting the 0.00. It tells the person who looks at the number what kind of measuring instrument, how much accuracy, how much confidence you have, how much significance you give each of these numbers when you're doing a calculation, which we'll do shortly. So if there's a decimal point like this, trailing zeros count, even if they're a little later. Like what if it had been on the exact 7.2? We'd add a 0. Because if we could read the 7 and we could see that it was on the 0.2 line, we still need to make our estimate and say, yep, it's right on the 0.2 line, so my estimate is a 0. If you thought it was a little beyond the 0.2 line, you would say 0.22 or 0.23 or something. But if it's right on the 0.2, you need to add the 0. And this 7.20, it's got a trailing 0, and it's after a decimal, so it is significant. Okay. Now, I want to show you, though, another way that you could, let me get these out of here because I just need a little space. That you could have trailing zeros that are not significant. Okay. So let's go back to that that original number in meters right here. Okay. So we had 0.0783 meters. So one of the things that we're going to do later on is work with wavelengths of light. And maybe you need a number in nanometers so that you can see where it falls on the spectrum, which color, is it part of the ultraviolet, infrared? Is it visible? What color? So if we're going to put this in nanometers, okay, we know that if we go from meters to nanometers, we learned this in metric, that a nanometer is 1 × 10 to the -9 meters. So I've got to take my original number and divide by 1 × 10 to the -9. And I end up with this. Hold on, I need them. That's how many zeros I need. I am not going to put a decimal place in that number. And the reason I'm not is that those are just placeholders. You see that? They're just holding the place. So because I put it in a unit that was really small, I needed a really big number. And so I needed some placeholders. If I put a decimal at the end, I'm indicating that I used some kind of measuring instrument that was good to the nanometer. I mean, we can't really have or access that type of measuring instrument. This number, 785, followed by a bunch of placeholders, still has 3 sig figs because the original measuring tool had 3 sig figs. Taking a measurement and putting it into a different unit by dimensional analysis cannot change the number of significant figures that are in that, that are in that number. Okay. So let me erase this, and I'm a little worried here. I think my note about it's kind of hiding things, and it's behind my. Sorry, but hint: change the number to scientific notation, and it's much easier to tell if a 0 is significant or not. Let me do that. Let's go back in a different color and put these into scientific notation, which we've also practiced and learned. So this is what, 7.83 times 10 to the -2. 7.83, they're all non-zero numbers. That's just like this, 3 sig figs. Okay. Even if I took this number and I put it into meters, it would be 0.0703 meters. Okay. Now here, I have a situation where the leading zeros do not count and the embedded 0 does. If I want to make that a little easier to see, I want to switch to the red pen because it's a little thinner. I don't have that much room. 7.03 times 10 to the -2 meters. Oh, and my negative is all over the. There we go. So you see, there's the embedded 0, and it's 3 sig figs. Scientific notation, I think, sometimes makes it a little easier. Look at this last one in scientific notation. So that one would be, let me count, 10 to the, gosh darn, I must be just kind of hitting a little hard. Sorry, pretty sensitive sometimes. So 7.85 times 10 to the 7th nanometers. You can see the 7.85 has the 3 sig figs. So now let me erase some things here. What I want to, there's a way to erase a little bit more efficiently. Sorry about that. And at any time during screencasts, if I'm erasing something that, you know, you wanted to take notes on, because it's always a good idea on a screencast, you know, take some notes so that you have them to study later and don't have to watch the whole screencast again. But you're always welcome to rewatch them. But you know, you can always pause a screencast if I take something away too soon. So, but here's what I wanted to say is that what I always tell my students is that, you know, you've got to worry about the zeros. And I kind of tried to underline and highlight them. I tell them to memorize this. Leading, never. Embedded, always. And then trailing, only if decimal. That's the only time they are significant. So, you know, remember that the non-zeros, you always count them. And then these other statements are just pertaining to 0 and its position within the number. So let's look at a couple of examples. Okay. Make sure we kind of, make sure we kind of understand these. So remember, leading or never. So that's why this only has 3 sig figs, the 6, 8, and 2. Embedded, they're always significant. So we're counting that 0 because it's embedded. It's between the 1 and the 7. Trailing, only if there's a decimal. So here, we're not counting those zeros. They are simply placeholders. This has 1 sig fig. Sometimes people ask me, well, how would you end up with a number that has 1 sig fig? Well, you know, maybe this is like a pressure gauge and it's marked off 200, 400, 600, 800, and they had to guess. They said, I think it's halfway between the 200 and the 400. I'm going to call it 300. That's a guess if there's no line to mark it off. Now this, if there's a decimal at the end, this indicates that you were using something where you could read the tens, you could read the hundreds, you could read the tens, and this is the estimate. So this would be, you know, like you can read 300, 310, 320, 330, 340, and they just had to estimate the ones place. It has 3 sig figs. A number like this one indicates that you could read on whatever scale this is. Maybe this is a thermometer, and you can read the hundreds, the tens, the ones, and the 10th is the estimate. So this would be marked off 300, 301, 302, 303, because the 10th, oops, and I'm not sure, I was going to say, I'm not sure what happened there. The 10th is the estimate, but we count the estimate as part of the sig figs. Remember that. It's all the numbers you're certain of plus an estimated digit. So, you know, because sometimes people say to me, well, like, you know, what's the big deal? Because, you know, don't all of these give you the same answer when you're calculating? I mean, like you're multiplying by 300, but we're going to take a look at how you use the sig figs to round off your answer. I'm sure all of you at some point have had a situation where you're doing something in math or science and you multiply and you get a number and it's point, 6, 8, 2, 3, 9, 5, 4, 3, 2, and you say, hey, where do you want us to round this off? Well, sig figs are going to tell you where to round off your answer. Like if I multiplied this number right here, I don't know why I can't. If I multiplied this, my answer can only have one sig fig. If I use this number to multiply, my answer can have 3 sig figs. If I use this one to multiply, my answer can have 4 sig figs. And then all of these depend on what the other number is. It tells me where to round it off. Once you learn how to identify the number of sig figs in a piece of data or a number, and you learn the adding and subtracting and multiplying and dividing rules, you're never going to have to ask your teacher, hey, where do I round this off? Now, you might have to ask us a little bit when you're learning it, but once you really get it down, you're not going to have to ask us a whole lot. Okay. Adding or subtracting, the last digit is retained. The last digit retained is set by the first doubtful digit. So, like you got a bunch of numbers to add and you line them up, okay? And you see here, you have a number in all of them, and the 2 is doubtful. So you have to round off to this place. Look next to the 3, there's a 7, so you round up, it's 8.04. Let me try and give you an example. Let's say that you use our large graduated cylinders to measure something. And the large graduated cylinder can only be read to the ones place, so you got to estimate the tenths. And boy, it looks to you like it is right on the 21 milliliters. And then you have to measure something else and add to it, and you use the little 10 milliliter graduated cylinder, which can be read to the tenths, so you can estimate the hundredths. And in that cylinder, it looks like it's between the 4.2 and the 4.3, so you make it this. And you added those liquids together and you get 25.25 milliliters. But up here, right, this was estimated, the 0.0. I mean, maybe it was a little above, maybe it's 21.1. Maybe somebody else like, I think it's a little above. I don't think it's right on the line. Somebody else says, man, I think it's a little below. I think it's 20.9. It's an estimate. You have to guess at it. So if we're guessing at the tenths place right here, if this is a guess, we can't have a hundredths place in our answer because the tenths place has a guess, has an estimate, has a doubtful digit. So we have to round our answer off to the tenths. I look at the next number, it's a 5, I'm going to round up. My answer for this would be 25. Whoops. Oh gosh. Hold on. Interesting. I'm just keep making it worse, don't I? Well, we're going with this now because we're almost done. 25.3 milliliters. Dang. So, okay. And I just can't seem to write milliliters on there. So there we go. All right. Our next slide is about multiplication and division. Okay. So when you multiply and divide, your answer may not have more sig figs than the least number of sig figs in the problem that you were, using. So get the highlighter back. You see here, this one has 5. Sorry, it's not a very good color for the highlighter, but now I don't know how to switch colors. And oh, wait, let's see. And this one has 2. So our answer can only have 2 sig figs. So we get this answer 4.59568. That's too many sig figs. We did not know this to the 5th decimal place. And I know sometimes people are like, why can, oh, so there's 1 decimal place for keeping 1. That's not the case. You'll see that as you go through this a little bit. It's how many sig figs. It goes on the number, not the decimal place. The adding and subtracting in that previous slide went on decimal place, 2 decimal places. And then in this slide, it has to go on how many. So like over here, we have 3 sig figs. We have 5 sig figs. We keep 3 sig figs in our answer. 7.1, that 0 is our last sig fig, but the next number is 9, so we round up. Neither of these numbers that we were using to get our answer was 2 decimal places. It doesn't go on decimal places. It goes on how many sig figs. And, you can try it if you want. You can try 45.3 and 45.1, and you're going to see that you can't keep any more than this because doubt shows up in the 2nd decimal place. So when you are adding and subtracting, you go with the decimal place where they all have a number. When you're multiplying and dividing, you have to count how many sig figs are in the numbers that you're multiplying and dividing and round your answer to that. So you should be able to define sig figs. All the numbers you're certain about in a measurement plus 1 doubtful digit, 1 estimate. Apply sig fig rules. Remember, the non-zero numbers always count. When it comes to 0, leading zeros never count. Embedded zeros always count. And trailing zeros only count if there's a decimal somewhere. And then you should be able to apply the sig fig rules when you're calculating. When you add and subtract, you have to have a number in that decimal place to keep it in your answer. When you multiply and divide, you count how many sig figs and you keep the least number of sig figs in your final answer. So good luck. There's going to definitely be, some practice problems for you to do. And we invite you to ask questions, as you might have them. So good luck with sig figs. Keep applying them to all the numbers you read and all the numbers you calculate with.